Hello, I'm Mike Wilbur, and I'm going to present our work on an online approach to solve the dynamic vehicle routing problem with stochastic trip requests for paratransit services. We are primarily concerned with two domains, dynamic paratransit and microtransit. We formulate these problems as a dynamic VRP with stochastic trip requests. And we present our solution, which is a fully online, non-myopic approach to this problem. Paratransit and microtransit offer door-to-door services through flexible, scheduled, and on-demand trips. Paratransit extends existing transit to residents with handicap or limited access. Microtransit extends paratransit-like services to all residents. Paratransit is considered a social good and is a required service in many urban areas in the United States. Paratransit and microtransit both add flexibility to existing fixed line transit systems, resulting in a more dynamic transit system. Vehicle routing can be thought of as a cyber-physical system with data streams such as traffic, weather, etc., and a set of resources, in this case, high-capacity vehicles. There are incoming trip requests, and the goal is to allocate resources in a way that accommodates the trip requests. This can be modeled in two different ways. A static VRP, we know customers beforehand, and the vehicles are assigned routes for that day. The dynamic VRP is an extension of the static VRP, which as vehicles traverse their routes, new customers arrive throughout the day. And our goal is to update vehicle routes to service these new customers. Dynamic paratransit and microtransit need to be modeled as a dynamic vehicle routing problem. Existing solutions aim to optimize a non-myopic utility function or batch requests together and optimize a myopic utility function. Paratransit and microtransit requests are generally sparse, which makes batching ineffective. Existing non-myopic solutions rely on models and value functions learned offline, which can become stale in rapidly changing conditions at inference time. In this work, we propose MCVRP, a fully online and non-myopic solver for DVRP with stochastic requests. We model the DVRP as a route-based MDP. Given an arbitrary state, we use generative models over customer requests to simulate the environment in future states and evaluate potential solutions with MCTS. To address the intractably large action space, we propose two heuristics that prune the search tree before running MCTS. In this problem, we have the following VRP settings. We know it's multi-vehicle, and these vehicles are high-capacity vehicles. Typically, somewhere between 8 and 12 passengers can fit on a single vehicle at a given time. The trip requests have both pickups and drop-offs, and there are time windows associated with the pickups and drop-offs, which are hard constraints. We also accommodate same-day requests. In this case, our objective is to maximize the number of trips served throughout a day. We model this as a route-based MDP. The state includes the vehicles and a new trip request. We have a weighted routing graph, which is weighted by the travel time between two nodes in a network. We also have the series of route plans for each vehicle. Each route plan consists of a series of locations where each location is a pickup or drop off for a customer. The action is a new feasible route plan for all the vehicles in the network, and we have a set of feasible route plans to be selected from. In this case, the rewards are 1 if the new trip request is included in the action, and otherwise it's 0. Our approach primarily consists of 3 components. First, we have the pickup and delivery problem with time window solver. This is a heuristic solver that enables us to check if the current request can be accommodated in a feasible route plan. The second component is based on feasibility graphs, which are used to score and sample promising actions for further evaluation with MCTS. The last component is MCTS Evaluation, which is used to further evaluate the promising actions in the context of future request demand. We'll start with the feasibility graphs. The primary problem is that the action space is computationally intractable. Our solution to this problem is to use cheap heuristics to select the K most promising actions. To select these actions, we build two separate graphs. The request vehicle graph, or RV graph, is a graph in which there is an edge between a request and a vehicle for every feasible route plan in which a vehicle can service the new request. The vehicle graph, or VV graph, contains edges between two vehicles, which represent the swap with the highest utility. In this case, a swap is moving one passenger that has not been picked up yet from a vehicle to another vehicle. In this case, a feasible action can be defined as any independent set of edges from the union of the RV and VV graphs that include only one edge from the RV graph. Our key insight is to use a cheap heuristic to score feasible actions. The heuristic is used as the utility of edges in the RV and VV graphs for selecting independent sets. The first heuristic is a budget-based heuristic in which we aim to maximize the time in which a vehicle has no passengers on board so that the vehicle is free to accommodate new requests in the future. The second metric is based on passenger travel time. In this case, the PTT metric aims to maximize the space available in vehicles to accommodate new requests. At the end of this stage, we have K feasible actions, which we're going to evaluate with MCTS. Our MCTS evaluation includes using event chains. Event chain is a sequence of trip requests sampled from the generative demand model. In our case, the generative demand model is a weighted aggregation of trip requests that can be sampled to generate these chains. We also rely on route parallelization. In this case, we sample many event chains and instantiate separate MCTS trees to process each of them. We then average the scores across the trees for each potential action to determine the action taken. We set up a series of experiments based on 129 days of paratransit trip requests from our partner agency in Chattanooga, Tennessee, CARTA. We vary the number of vehicles, and also the requests arrive 60 minutes before the requested pickup time. The pickup and drop-off time window is 15 minutes before to 15 minutes after requested time. Since the data did not include a requested drop-off time, to ensure quality of service, we set the requested drop-off time to be the requested pickup time plus the direct travel time between the pickup and drop-off. We compared our approach to a series of baselines. First, we have two versions of our MCVRP approach, one with the budget heuristic and one with the passenger travel time heuristic. We also created two greedy approaches based on our budget heuristic and our passenger travel time heuristic. We also compared it to DRLSA, which is a non-myopic deep reinforcement learning approach. Lastly, we also compared to MARTV, which is a myopic batching approach with RTV graphs. In this figure, we compare the service rate for MCVRP to the baselines. Our approach with the budget-based metric has the highest service rate, followed by MCVRP based on the passenger travel time heuristic and MARTV. We also look at the computation time. One issue with our fully online approach is all computation occurs at inference time, which can result in issues with computation time. Therefore, we look at first the CARTA data set. The median time between requests was approximately 5 minutes. Also, 99% of requests arrive more than 30 seconds after the previous request. In the case of MCVRP with the budget heuristic, the computation time per request varied between 38 and 49 seconds. It's important to note that MCTS can run in the background as the operator takes requests. Our approach is also an anytime algorithm, which can be stopped short as needed. We reran the experiments with 30-second cutoff time for MCVRP. We show that the cutoff time had minimal impact on performance. We also compared our approach in the context of robustness. The goal of this experiment was to evaluate approaches to changing system dynamics at inference time. We used real traffic data to update travel times along road segments to represent congested roadway networks. We can see that our approach had less of a change in service rate between the original experiment and the experiment run with the more congested network, showing that MCVRP is more robust to changing road conditions compared to the baselines. In this work, we provided a fully online, non-myopic solution to the DVRP with stochastic trip request problem. In future work, we look at adapting our approach to a hybrid model to save computation time, as well as looking at decentralized approaches. We are currently working on a software platform to be used by our partner agency for paratransit and microtransit services. Thank you.